Okay, let's start. Hi everyone, my name is Marian. I'm a software architect at NVIDIA networking unit. And today I want to cover a few topics with regarding to SAI and running SAI on DPU. So we are going to touch upon three subjects. First, we will take a look at the general architecture of the DPU and the use cases that it covers. So basically, seeing where it can fit and what it solves in the network. Next, we are going to look at the ways at how we can implement a new overlay pipeline for SAI for DPU. What are the APIs and also infrastructure for that, and what are the differences from the network switch as well. And also, as the last but not least topic, we will cover the elements that are more common to the DPU, like stateful tables. I wouldn't say they are exclusive to the DPU, but they are definitely more common. So when looking at the DPU architecture, so let's start first with the definition. So DPU, data processing unit, or a smart NIC, as some people call it, is a network device that bears the responsibility of offloading all network-related functions onto that device and leaving the connected server the connected server CPU only for the compute tasks. So we end up with this clean, disaggregated approach where the host is only doing the host-related tasks. DPU takes upon all of the network tasks. So one thing to notice here, the link between the server hardware and the DPU hardware, it can be both physical and logical or virtual. So in some cases, the DPU can be physically connected via PCIe interface. In that case, it is more referred to as a smart NIC. In some other cases, it could also be that the DPU is sitting somewhere separately in the network from the host, but still it is serving that host and potentially more than one host. In that case, a DPU sometimes is referred to as an appliance. But in any case, the main role of serving the network tasks to the host stays the same. So there are different roles that a DPU may take. So it provides a bunch of different acceleration engines, also an ability to run the full control plane, as I mentioned, because it can be just a separate appliance. So we can spin network OS on that and do a bunch of things that were previously a responsibility of the hypervisor itself. So looking at the use cases, we can define a few main sections. Today we will focus on the network itself, but you can mix and match, and you can define your new roles in the network. So there can be a security offload, like you can do encryption with that device. You can relay key management to that. You can also do some of the network offload. That what I mentioned previously is a custom pipeline definition. So it provides you with all the programmability tools to define your own pipeline and even more than one. So we'll see how we can do that in SAI. You can also do some stateful stuff, as I mentioned before as well, like connection tracking, which is quite relevant when we're talking about hosts. And storage offload. As well, there are some use cases. So in case the DPU is providing an end connectivity to the storage-oriented devices, then possible use cases there with engines like compression and other stuff. So now let's move on to SAI. So when looking at SAI API and the behavioral model that it provides, so first thing that you will notice for the switch, it's quite common, and the reason for that is that because switch SAI is defined according to all the IEEE standards, meaning that we don't really need to invent a wheel, but basically we are just following those standards and putting them on a paper in the form of SAI APIs. We know exactly where the bridge sits, we know exactly where the router comes into play, how they interact, and so on. When we are talking about the DPU pipeline, it's quite a different use case, because depending on how you build your network, depending on where it sits, it can define a completely different packet processing pipeline for all of those roles. So, but first, we want to actually use as much as possible from the standard SAI. As I mentioned, SAI today defines a bunch of IEEE standards, including, for example, layer 1. So we want to utilize all of that. Basically, what is mentioned in here as underlay is all of the SAI API that will provide connectivity to the TOR. So every DPU will be somehow connected to the rest of your network, and we need to provide that part of connectivity and configuration to the TOR. So this includes the port APIs, the ASIC, or what it's called the switch APIs as well, so you can configure some global attributes. And also things like host interface. So the DPU itself is host interface, so we can utilize those APIs as well, and also all the functionality that it brings in. Like you can even run some protocols on top of that. Like you can advertise to the TOR your IP, stuff like that. So this is the first part, which is common. What is required from vendors basically to support that we can bring it up, we can configure the ports and have links up and connectivity from the TOR. We can basically, let's say, ping our DPU. So this is step number 1. Step number 2, or block number 2 that we would need to have, is a custom pipeline. So this is something that will be interchangeable. So some networks will use one pipeline, some networks will use another pipelines. Like if you compare edge to your core network, definitely there will be differences. So we don't want to enforce any particular pipeline, but what we want to do is to provide with a way to to load a pipeline into SAI, or define a pipeline into SAI, and in the future potentially load it as well. So this is done in 3 steps. As I mentioned, first step is every overlay table is defined as SAI extension. So we are going to use SAI extensions to define our table. So looking at the slide before, we may come up with some new entities and new abstractions for the DPU, which are more host-oriented, like, for example, a definition of the VM, so we can perform our operations in the context of the VM. It could be direction aware, so we can also define some direction lookups and then different ordering of the tables, some other stuff, map it to the underlay, and so on. So each of those abstractions is represented as a SAI extension, and every such match action table is a new SAI extension object. So this is not really a new thing. SAI already provides an infrastructure for that. We want to utilize it. Then step number 2, as I mentioned, there are many pipelines possible per use case, and only one extension is valid at a time. So you can basically use one pipeline at a time, but they can be interchangeable. And step number 3, this is something futuristic that we are looking into bringing into SAI someday, is how you actually define connections between those tables. Because if you look at this picture, what SAI allows you to actually define are APIs for each table. You cannot tell SAI how you actually order those tables. So SAI will not provide you with information which table comes after which table and what is the order of them being applied. So we want to also in the future enhance these APIs to be able to load this order of the tables or load the pipeline into SAI, providing it with a way for better for the implementation of that SAI adapter for better understanding of the pipeline. So it does not have to be assumed with the implementation, but instead we can load it and use some different tools to actually provide instead of hard coding everything, we can use the tools use some tools to generate those tables. Next, so those were two first building blocks. They are more or less straightforward, but then looking at the use cases for DPU, we outlined another kind of, let's say, a primitive that needs to be supported by SAI if we want to satisfy all of those scenarios for the DPU. So for example, DPU may perform the following network functions in your data center. It can do a stateful firewall, like for example, only allow connections to go one way, and if this connection is open, then it will open it in the other direction. Dynamic net, fully done in the data plane, no interaction with the control plane. So all of the entry allocation will be done in the data plane, allowing for basically millions connections per second running. Some QoS as well, like flow burstiness, flow caching for better allocation of the resources within your network. You may cache some of the operations using those tables. Stateful load balancing, also an important use case. According to the studies, almost 40% of the data center traffic is being load balanced. So this is an important role and someone needs to do it. And a DPU is a great candidate for that. But again, if you want to provide a per connection consistency, you would need to, one way or another, remember your connections. You would need to keep them persistent when you update the pool of VMs and so on. So what we want to achieve is actually to define a SAI abstraction that can implement any of those use cases without actually hard coding them in SAI, if you wish. So to do that, let's first define what a stateful table is. A stateful table is, or what some people call it, a stateful ACL, is next iteration in the hardware ACLs, which the main difference here is that they perform a learning on their own. So you don't need to use control plane to actually learn new entries in this table. So basically, any of those use cases can be satisfied by control plane programming a stateful table, let's say, how it looks like, how it needs to behave. And we will talk about all of these components in a minute. And then it will take upon all of the rest of the operations, all of the time-sensitive operations it will perform in the, basically with the wire speed. So what we need to actually how it works basically similarly to the ACL. So first step would be for us to define the flow key. So simple examples would be a 5-tuple if you want to do connection tracking. Also, you need to pay attention to direction awareness of this key, because there is this connection has source and destination swapped depending on the direction and so on. So we need to take that into account. Then the table itself, its attributes, and the state and the operations performed on that state for each flow. So the responsibility of the control plane would be to basically load some, let's say, executable code that will be executed upon every packet event coming for that flow. So table may or may not learn every new flow. So what is the event for the table learning that flow is when we have a miss on the table. Let's say we reached our stateful table. It has already some entries. Our key does not match any of those entries. It means that we have a miss, and on a miss we will go to the start state, and the table will decide if it wants to learn that connection or not. So simple example would be like if we're doing connection tracking, we only want to learn connections starting with the TCP SYN. We don't want to learn them in the midst of the open connection. So this is the learning process. Control table, you see that the interaction with the data itself is pretty minimal, so it needs to program all the parts and then leave it be. But however, it's not necessary. So I'll give you an example. You are all familiar with the concept of FDB in the switches. It's the first trivial example of such a stateful table that performs learning. But still control plane may interact with that. First by actually being notified about all the MAC entries learned, and second by programming static entries. So control plane in a general use case, talking about stateful table, is also allowed to program static entries in those table if needed, maybe even interact with this state of a particular entry as well. So what we need to define in order to make this table functional, first is match key, as I mentioned. It will define what is our flow. So this is what will be parsed by the parser, and what will be matched against our table. So pretty trivial, not really different from ACL, but still there are some differences. Then the state graph, and this is basically the code to execute all of the states, their callbacks. Basically, we're implementing a kind of a paradigm for the state machine in the software engineering. Then, since we have a table that occupies space in the memory of our network device, we need to define a size for it, so we will know exactly how many resources those entries will occupy. And since the control plane doesn't take part in the programming and removing those entries, we need to specify it with the eviction policies how exactly those entries will be removed. Like, for example, it could be when the table is full. You can basically say there's an LRU policy and remove that particular connection. Then context. So the whole idea of the stateful table is that besides the entry itself, there is a context that persists, because it's not operating on a packet basis, it's operating on a flow basis. So we need to keep a context of that flow in between those packets. So this is something that SAI needs to provide a way to define a context, so that this context memory will be allocated for every entry in the table, and then it will be persistent, and the state graph can actually utilize that context, like write into it, read from it, and so on. And control plane also may interact with that context if needed. And the timer. So we were talking about one kind of events, which is packets coming in, then they are parsed, key is extracted, and it is matched against the table. So this is one kind of event. Another kind of event is a timer, because since we're talking about flows that persist across packets, it is also very important to have a way to define some timing events. Like, for example, if you want to age out your flow and remove it on that basis as well. So what we're trying to do right now, we want to define this kind of object model for SAI that will give you all the building blocks like we have today with the ACLs. You can define key, you can define actions, and so on. We want to come up with this object model for the stateful tables that will allow you to bring this all pieces together and basically have your network function running on your network device, on the DPU. So let's start with the first thing. How do we reach our table? So there is no notion of a stateful table in SAI behavioral model today. We need to somehow point to it. So first, probably the first thing that we will try to do is to go to that stateful table from the regular ACL table. Like simple example, ACL table looks if it's a TCP packet. If so, then go to my connection tracking table. Then the stateful table object itself. It has all of these parameters that I listed, and we need an object for the context. We need some way to define a full structure. It can't be a fixed structure, so we need to define some flexible structure, and also we need to define a memory pool, similar way to what we have in buffers. Today in SAI, we can allocate memory for buffer pools and so on. So similar thing here, we will tell how much memory we will allocate for that. Flow key, you can see more than one because it can be direction aware. So, and also they can be completely asymmetric. Again, going back to the FDB example. First, when you learn your connection in terms of FDB, which is your port MAC, you learn MAC with the source port, but then when you want to do a lookup to find out where packet with this MAC through which port it needs to go, you will actually need to get a destination port as a result. So there are different permutations, and we need to allow for more than one key because of the direction awareness. Then the graph states and timer graph states. So we need somehow to define all of the state machine for every entry and be able to load those callbacks to be executed, and so that this will allow for the stateful table to operate on its own without control plane intervention. So our call to action is very simple. Please join the review of Stateful SAI API proposal. So current state as of today is that we have provided the list of requirements. You can review that in the November timeframe. We are actually going to put this object model into a code and start reviewing that within the SAI community. So thank you everyone, and please join this join the review process of this new proposal. Thanks. Any questions? 1, 2, 3. Solved. Okay.
How would you relate this to previous efforts like FlexSci, and how do you relate this to Sonic pins with P4 programmable parts of SAI? Put that in perspective.
Yeah, so there are some similarities. However, Sonic pins defines, again, it is a pipeline for switch at the moment, so it still kind of defines a single pipeline. Slightly different from what we are doing now. It also allows for extensions if you look at the PIN's proposal for SAI extensions for P4 as well. We have Flex SAI there, but those are just the tools that allow you to extend SAI. We are going to actually use SAI extensions themselves, which are the piece of SAI infrastructure, not some particular tool. Main goal for us is to allow for this kind of plug and play mode for those pipelines, because we may not know for sure which exactly pipeline you will need. So it's not like we are trying to come up with a single pipeline, but rather with a way for you to plug in your own pipelines.
Will there be a commercially available implementation of this sometime soon?
Yeah, so we are working also with other companies on projects like Dash that want to introduce the SDN pipeline. There may be more. Okay, thank you very much. I want to